Hi everyone, my name is Pariya Yousefi. I am an undergraduate student at Concordia University, and in this video I am going to explain my internship project, which is about perovskite crystals. First, I will introduce you to perovskite before I explain about my project. Perovskite is a naturally occurring mineral of calcium titanate with a chemical formula of AbX3, where in this case A represents calcium, B is titanium, and X is an oxygen atom. So, looking at the general formula, you can see that a large number of different elements can be combined together to form perovskite structures. Other than compositional flexibility, there are other properties that are unique in perovskites. They have a tunable band gap, they are easy to make in the lab, and also they have a high defect tolerance.
What is a band gap and why is it advantageous to be able to tune it?
The energy difference between the valence band and conduction band is called band gap. Now, different ions have different energy levels between the valence band and conduction bands depending on the number of the orbitals and electrons of them, and that's what I mean when I say tunable band gap. For example, here you can see that if the anions change from the chloride to iodide, the band gap will be different since they have a different number of orbitals and electrons. Upon the photoexcitation, the electrons from the valence band are going to be excited to the conduction band. With this event, there will be free electrons in the conduction band and hole in the valence band. Now, for applications such as solar cells and electricity, the electrons and holes should be separated to create a current. This is done by attaching these materials to the electrodes, which are cathode and anode. Now, for certain applications such as lasers, we don't attach electrodes, and as a result, the excited electrons are simply going back to the valence band and release energy as photon. As you can imagine, based on their properties, perovskites are being used in many applications. For example, they are being used in lasers, LED, solar cells, and even biomedical applications such as X-ray and imaging purposes. Now, here comes to my project, where I focus on modifying the structure to replace lead with other cations. And also, I try to increase their stability and efficiency with many different ligands and propose a new synthesis for it. But first, let me introduce you to one more thing, which is the difference between single perovskite and double perovskite. Double perovskite is an extended version of single perovskite, and as you can see from the general formula, every ion in the unit cell was doubled, and hence it's called double perovskite. The new structure has more potential to incorporate more metals in it, and we can now have more options to replace lead with. Double perovskite are also air stable, and not only they have a long emission lifetime, but they also have excellent optoelectronic properties. Being able to predict and determine the stability of double perovskite before synthesizing them can be very useful, as we can avoid spending time on making something that is not going to be stable in the environment. For this reason, I approach to use a new tolerance factor formula that will help to predict the stability of the double perovskite. This is a modified version of Goldschmidt tolerance factor where both size and oxidation number of the ions will be considered in it. Here I am showing you just some of the tolerance factor calculation of double perovskite that I calculated. Based on this new tolerance factor, if the answer is less than 4.18, it means that it's a great possibility that the perovskite is going to be stable. However, if we get a value higher than 4.18, there is a great chance that our crystal will not be stable.
So what considerations would you have to take into account if you were to introduce a new cation to your double perovskite?
Since we're trying to introduce a new cation into the perovskite structure, it is very important to consider about the size of it. Because if the two cations have a very different sizes, the perovskite structure might not be formed because the bonds cannot be formed properly and crystal is going to collapse. Based on the tolerance factor calculation and other factors such as size of the cation, I decided to choose this double perovskite with the formula of cesium-2 sodium erbium chloride 6. Then I propose a synthesis for it with the proper salts and capping agents. The steps for this specific process are shown here, and in this case the perovskite is going to be formed once the cesium alloy is injected. After that, we can take the round bottom flask from the hot plate to stop the reaction for further going, or we can keep it for longer time on a hot plate if we want to have a crystal with a larger sizes, as both temperature and time can affect the size. We can quickly see if the synthesized perovskite is fluorescent or not by checking it under UV lamp. And as you can see here, it is fluorescent. The final step is to separate the perovskite and solvent from each other, and this is done by the help of centrifuge, which apply a gravitational force that causes perovskite, which has a higher density than the solvent, to sink and precipitate out. Now that we have our perovskite, we can analyze the properties of it, and one of the important characterizations that can be done is measuring the absorption and emission of the crystal. This can be done by using fluorometer. A fluorometer will illuminate light at a specific wavelength to our sample, which is placed in the cuvette, and this will cause the electrons in the material to be excited. Then the detector can measure how much light is emitted from the sample. The perovskite that I made in this case has a photoluminescence intensity at a wavelength of 390 nanometer when it is excited at 360 nanometer.
Why do we see a shift between the absorbance and emission maxima, and what causes this energy loss?
Great question. Based on my previous explanation, the energy of both emission and absorption should be the same, and hence they both should have the same wavelength. However, this is not always the case, and as you can see from the figure, emission and absorption wavelengths are different. And this is due to the fact that there are some vibrational levels in the conduction band, and as the excited electrons are going back to the ground state, some energy will be lost within those levels in a non-radiative form such as heat. And then the rest of the energy will be released as a photon. I hope you enjoyed watching this video and learned a little bit about perovskite. Bye!